gaseous exchange. Okay, and this time round we are going to talk about gas exchange. In fish, we saw how amphibians do carry out their gas exchange, how they obtain their gases. The three modes of gas exchange: the skin, the buccal cavity, and the lungs, the pulmonary ventilation. We saw how insects do their thing, and I hope you are an expert as far as insect gas exchange is concerned. We saw how simple organisms, in other words, it is a series we are moving on smoothly. So today, under proceeding lessons, we are going to see how fish, okay? We are going to see how fish and the different types of fish. You know, fish have different types. The two subtypes, the chondrichthyes and the osteochthyes. Those, the way they carry out their gas exchange, you are going to see all that. Okay? And in today's lesson. Now, this might appear common knowledge, but it is common knowledge. Let me also say that it's common knowledge that water is denser than air. That's why when you get an empty bottle and you pour there water, water settles at the bottom and air keeps on being expelled to top levels. Otherwise, if air was denser, then you'd pour water in the bottle and water floats, water just floats on top of the bottle. But anyway, that's just, let me say, common knowledge. So water is denser than air. So therefore, to be able to breathe within that water, then you must possess features, okay, that can facilitate you to extract the air that you need from the water. Okay? So water is more dense than air, it's more viscous than air, and the oxygen concentration in water is less compared to what is in air. The rate at which air diffuses in water is less compared to how it is going to diffuse in air. And we talked about this when we were comparing the media. And so what does that mean? That implies that for you to be able to live in water, you must possess features that will guarantee you to extract the air from the water regardless of this. Not so? And so if you are to compare these organisms that do stay in water, for instance, fish, amphibians, but those ones can stay both on land. But for fish, they are less active as compared to the organisms that do stay on land, to the terrestrial organisms. Not so? Why? Because the rate at which you can get oxygen, okay, from the water, it's hard to extract the oxygen. However, the high density of water, it is not taken for granted, in that it supports the gills. Remember, these organisms, they obtain their air through gills, and the gills are their respiratory surfaces. So the high density of water supports the gills from collapsing. That's why when you remove a fish from air, the fish collapses. The fish dies. Why? Because the gills, they won't have that support. Okay? They won't have that support. So they will collapse, and so they won't be able to receive the oxygen. Okay? They won't be able to receive the oxygen, and so they will die. So like I said, our fish are divided into two groups, and the first group, it is group cartilaginous or group chondrichthyes. Okay, now these are cartilaginous fish. They don't have bones but rather cartilages. Okay, so they are classified as chondrichthyes, okay, or you can commonly call them cartilaginous fish. E.g., we have a dogfish and a shark, and most of you know a shark. So I know you've ever seen this somewhere. This is common. So this is a shark. So it is under group chondrichthyes. Then we have another group of bony fish. Now these ones have bones, or you can call them teleosts or osteoids. So whichever word is easy for you, is what you go with. And these ones, they are the common fish on market. Somebody wants me to say fishes? It's okay. So these ones, they are the common fish on market. And we have tilapia. I hope all of us know what a tilapia looks like. Is it here? No, we don't have. No, in this one? No, it's not there. We have a tilapia. We have silverfish. Do we have silverfish? No, we don't have mukene here. Then we have Nile perch and mudfish. So the common fish on market, okay, they are all bony fish. And so these two groups, they are not taken for granted as far as obtaining gases is concerned. The difference is not just bonds, but also the gas exchange. The way they obtain gases is way different among the two fish, the two types of fish, or the two groups of fish. Not so? And each is adapted differently. For example, yes, they might all use gills, but first of all, the gills are different in the two groups. The gills in chondrichthyes, they are different from the gills in osteoids. Even the mode of ventilation, the way they do obtain, the way they do extract the oxygen from the water is different. Not so? So let's have a look at group chondrichthyes. Okay? Let's have a look at group chondrichthyes. And if you've been watching movies, if you are good at movies, or if you are good at touring, moving around, and you've ever seen a shark, then you saw such slits. You can have a look. You saw such slits. Now when you try to open this slit, you see something of this kind. You see something of this kind. Okay? And these are the gills. Okay? And these gills, they are the ones that do carry out gas exchange. So this is the surface for carrying out gas exchange. And if you know your normal teleosts, your normal fish, the osteoids, they don't have such slits. If you have ever seen a fresh fish, they don't have such slits. It is just one ridge, like this, and it's rigid. Okay? This ridge is called opachinum, and it's rigid. Then it's what you open, and you find gills inside. So do you see? their structures are different. Not by coincidence, not that that's how they were made, but I think it has something to do with evolution. For us who believe in evolution, probably it has something to do with evolution. Not so? Anyway, let's have a look at that. Let's have a look at the cartilaginous fish gill and see. Now, on each side of the pharynx, you have there 5 pairs of gills situated in pouches. So these are the pouches. Where is my pointer? It is disappearing. Oh my god. So the gills are situated within the pouches. Okay? And these are the pouches. These ones. So this one, this one, this one, this one. And there are 5 of them. However, the 5th is modified into okay, it's hard to recall the word, but there are 4 of them which are functional and the 5th is not functional. Okay, so there are now these pouches that do contain the gills, like how you can see. Now the gills, obviously they are numerous leaf-like structures. Okay, very many leaf-like structures called lamellae, and actually there are those lamellae that do have sites called gill plates that do have sites where real exchange occurs, and we are going to see which sites are they. So they project horizontally from a branchial arch. We are going to see the structure and I'll show you each of these from a branchial arch. Now the arch, it is made up of a cartilage, and it is that arch which supports these gills. Okay, and the gills, they do project horizontally from that arch. Now between the 2 gills, or between the 2 gill lamellae, okay, you have there, let me call some fibrous thick structure that supports these lamellae. Okay, and it separates the 2 gill lamellae, and that structure is called a septum. You remember your septum of your heart? That's good. You remember the septum of the heart, which separates the 2 ventricles? You remember? Yes. Also, this septum, it separates the 2 gill lamellae. In that, if you have your lamella that stretches like this, and you have another lamella that stretches like this, then you have some fibrous structure, okay, that stretches from this end to the distal end, and this structure is the septum, and it will separate the 2 gill lamellae, and it supports them, by the way, not just separating, but supports them. You remember these ones, they are just, you can have a look at this. They are structures where exchange is going to occur from, and they are just suspended. Now if you don't support them, then how easily is water going to pass through? Won't they collapse? So now this septum, or these septa that are between these numerous gills, they do provide that support to the gill lamellae. Okay, now the septum, I think it is the next sentence. Let's go word by word. Now that septum, each septum projects beyond the distal end. That's what I wanted to illustrate. I even illustrated it. So if this is one gill lamella and this is another gill lamella, okay, then the septum projects beyond where the gill lamellae stop, okay, to form something of this kind. Now this is what we call a branchial valve. Okay, it's a branchial valve. Now that valve is the one which determines it controls the opening and closure of the gill slits, these ones. Okay, when is it going to be opened, when is it going to be closed, so that you maintain the water flow to either allow efficient diffusion, to get enough oxygen that is required by such an organism. You can see how huge it is, and then you get rid of carbon dioxide. Then you have numerous vertical plates known as gill plates. Yes, I talked about gill plates. Now these are the plates, these ones. They are found on the gill. So if this is the gill lamella, and this is another gill lamella. Now on the gill lamella, you have their vertical plates. They are like, okay? And there are numerous of them. Numerous, very many of them. Now these vertical plates, they are the ones that actually do contain numerous blood capillaries, okay, that span through this. They span like this. They span like this. Now water that is passing through these lamellae, it also passes through these gill ports, these spaces in between, so that you have a direct contact between the blood capillaries.
So the blood mixes with the water.
No, blood cannot mix because blood is confined within capillaries, and the capillaries are confined within these gill plates, and the two are separated by just a thin layer. I think it is even just one layer of epithelial cells. So just a thin layer of cells, okay? So that they are in close contact, but obviously blood is confined within capillaries. So they are in close contact in that as water is passing through, okay, then blood is also passing through, so that the two are in close contact to exchange their gases. So those are the gill plates, and they are the same as far as the osteochthys gill is concerned. Then at the base of each gill, it's a pair of afferent and efferent
Okay.
arterioles. Yes, it's a pair of afferent and efferent arterioles. Now these ones, they are arterioles. If this is, we shall have a drawing. It's there. So these ones, the afferent, they take in deoxygenated blood to the gills or to the gill lamellae, and then the efferent, they take away the blood that is now rich in oxygen to collect up in the pulmonary vein, and then you transfer it to the entire body, because the fish has one single saturation. It has single saturation. You don't go back to the heart. So it is not the pulmonary vein, it is still the aorta. So you take it to the entire body for exchange to occur. And then this afferent, it is receiving blood from the heart. Okay? So the blood is deoxygenated. And then to the gills for exchange to occur. And you take away the carbon dioxide. So, but within, now these efferent, these branchial arteries, when they reach the gill plates, they branch into very many. Let me actually call it a network of fine blood capillaries. Very many. It's a network within the gill plates. These gill plates. Now, why are you branching into a network? Because you want to increase that surface area over which exchange is going to occur from, so that you extract enough oxygen from the water, and then you take away enough carbon dioxide from blood, so that by the time you reach the other end ridge, you have extracted enough oxygen to take the oxygen to the entire body. Not so? Yes, so it's a network of blood capillaries, the gill plates and the gill lamellae, where exchange is going to occur, and the exchange is down the concentration gradient, whereby the oxygen moves to the region where it is, from the region from where it's high to where it's low. That is what we call down the concentration gradient. And the carbon dioxide also moves down the concentration gradient, whereby in water, where you have much dissolved oxygen, the oxygen diffuses from the water, okay, into the blood. And then in blood, where you have much carbon dioxide, the carbon dioxide diffuses away, not so, and dissolves in the water and taken out through the opening. And you excrete it out. So basically this is the basic structure, and I got this from FA, function approach. That's a reference. You can go there and have a look and read through all this. So now you can have a look. This is the lamella. This is one lamella, another one. So these are geolamellae, and the two, you can have a look, the two adjacent, they are separated by a septum. So this septum, and the septum extends past just the gills to form what we call a branchial valve. Okay? Yes. Then the gill lamellae, they do have the plates, the gill plates. And if you try to magnify this, this is what you see, with numerous blood capillaries. These plates, they do have numerous blood capillaries, so that you increase the surface area, okay, over which the diffusion of gases is going to occur. Okay? And you absorb enough oxygen, and then you give out enough carbon dioxide. Then this is the gill bar. In this case, it's the gill arch. Okay? It is the one which will support this gill lamellae to stand. And this is our cartilaginous, this one, where the septum originates from. It is cartilaginous, and it supports, okay? It supports the gills to stand. And then you have the afferent and the efferent blood vessels. Now in this case, which one? Which one are you going to consider? But it might not be observable. Is it labeled? Yes, it is labeled somewhere. Where? So the branchial cartilage, you have the afferent, I think. So anyway, you have the afferent, the one which takes in, okay? It brings the oxygenated blood and then distributes that blood throughout the entire gill lamella, or the entire gill, and then the efferent arteriole takes away the oxygenated blood to the aorta, because they are just branches of aorta, and then the aorta takes to the entire body. Now this is a single saturation. The aorta will take the oxygenated blood to the entire body. So the efferent, they are the same as the efferent and the afferent vessel in the kidney, if you still remember that. Actually, yeah, if you still remember that. The efferent and the afferent vessel in the kidney, they all do perform the same. So let's talk about the mechanism of ventilation in our chondrichthyes, in our dogfish. And the mechanism is just simple. The fish opens the mouth, swallows water rich in oxygen, and then closes the mouth, pushes the water through the gills. And in the gills, gas exchange occurs, Okay? And when gas exchange occurs, the blood extracts oxygen from the water and takes in the carbon dioxide to the water. Okay? And then the water that is now rich in carbon dioxide is pushed outside the gears. That is just the concept. That is the concept. Now the next thing, it is also the other concept of pressure versus the flow of air and the flow of liquids. Okay? That concept. Liquids always flow from the region of high pressure to the region of low pressure. The other illustration I gave you when I was fetching water, that tube. Water flows from high pressure to low pressure. So anything now here is pressure changes and then water movement and then exchange. So I don't see why you people should find things hard. Things are easy. That is if you want to take them to be easy. And things will be hard if you want to take them to be hard. So let's start with inspiration. And what happens with inspiration? The flow of the buccal cavity must be lowered. And how is it lowered? The muscles that are attached on the buccal cavity, they are the ones that control the movement of the buccal cavity. Where you have the hypobranchial muscles and the transverse muscles. Now, the hypobranchial muscles contract and the transverse muscles relax. And when this one happens, when these ones contract, like I told you the same concept when we were studying about the sternoid and petroid in the fish, in the amphibians. When a muscle contracts, it shortens and stiffens. It becomes stiff and short. But when a muscle relaxes, then it elongates but loosens, slackens, depending on. And you can try that with your arm. You know the biceps and the triceps. You can try it with your arm and touch which muscle is now stiff. Then you straighten your arm and touch which muscle is now stiff. So that one. There you can understand. When a muscle contracts, it shortens. So when the hypobranchial muscles contract, they are going to pull the lower jaw, okay? And the flow of the buccal cavity or the flow of the mouth is going to be lowered. And if it is lowered, what is going to happen? The volume inside the mouth is going to increase. And you know volume and pressure, they are inversely proportional. Is it Charles's law? Anyway, you can check in the chemistry. But volume and pressure, they are inversely proportional. So if volume in the buccal cavity increases, then pressure decreases. Not so? And so when pressure decreases below the atmospheric pressure, then what is going to happen? Water is going to enter into the buccal cavity via the mouth. Because now in this case, the mouth is going to be open. But now for chondrichthyes, the dogfish, the shark, they have another opening. Okay? On the lateral sides of the pharynx, called the spiracle. So this opening also allows in water to enter. So water is going to enter through the open mouth and the spiracles. So now, after water enters the spiracles, exchange won't take place where? In the mouth. Then you have to close the mouth and you close the spiracles. They are valves which control the opening and closure. Okay? So, why are you opening? Because you're going to raise Okay? You're going to raise the flow of the buccal cavity. You're going to reduce the volume in the mouth cavity. And so if after reducing that volume, pressure increases, it will tend to increase past the atmospheric pressure. So if you leave the spiracles and the mouth open, then water will flow back. So therefore you have to close the mouth and the spiracles. Then you raise the pressure, okay, in the buccal cavity to be higher than the pressure in the opercular cavity. So that now water is forced to move to the gills. Here you don't have the opercular. So water is forced to move through the gills. So the flap valves open and the flow of the buccal cavity and the pharynx is raised, which forces water to flow through the gills and the respiratory epithelium of the lamellae, which is the gill plates. You saw the gill plates. They are the exact surface. Yes, we've been saying that the gills is the respiratory surface, but the gill plates, they are the actual sites where gas exchange occurs. So in this case, the gills are the lungs, but not the lung, but rather the alveoli, those sacs. So if you want to be more fancy, you instead, if somebody asks sites for gas exchange, you can gill plates. There you are specific. You know what you are talking about. So as this water that is rich in oxygen is flowing past the gill plates, then it will be in close contact with blood confined in the blood capillaries. And so what will happen? The respiratory gases, they will flow down their concentration gradient. Whereby oxygen, for instance, it will diffuse from water that is rich in oxygen to blood that is deficient in oxygen down the concentration gradient. Where now in blood it will combine with hemoglobin to form oxyhemoglobin and then transported to the tissues. And then in the tissues, you have there more carbon dioxide than oxygen. So the oxygen will diffuse from blood to the tissues. And then carbon dioxide, it will diffuse from the tissues to blood down its concentration gradient. And then what happens? Blood will sweep, will move through the heart and boom, to the gills. Where in the gills, in the gill plate, the blood will be in contact with water that is rich in oxygen but deficient in carbon dioxide. Then carbon dioxide is going to diffuse down its concentration gradient into the dissolved water. And then expiration. As simple as that. Now with expiration, you are pushing water out of these gills. You are pushing water out of these gills. Okay? You leave the operculum. It is not this. You leave the operculum. You are pushing water out of the gills. And what is going to happen? Still pressure changes. Okay? The transverse muscle, they will contract in this case, and the branchial muscles, they will relax. Then the flow of the buccal cavity is going to move up, is going to be raised, okay, due to contraction of these muscles, of the transverse muscle. Now if the flow is raised, what happened to the volume? Volume of the buccal cavity is going to reduce and pressure is going to increase. So what will happen? Water is going to be pushed through the gill pouches the other openings on the either sides of the pharynx. Okay? Through the gill pouches and then out through gill slits, the other lines you saw. And boom, water is out. And then the cycle is repeated. That is, if the fish wants to obtain more oxygen, and it's obvious case, it must maintain that constant supply of air. As simple as that. So can I receive some questions? So basically that's how these convicts obtain their oxygen and they get rid of their carbon dioxide. Now, as I was discussing, I said that the way these gills are arranged, they are arranged in a way that the water that is flowing through the gills together with blood that is flowing through the gill plates or the gills, they flow in the same direction. So the exchange is parallel. That flowing is called parallel flow or concurrent flow system. Okay? Exchange where both fluids are moving through the same direction. Think about that. Think about it. Does it have some challenges? Is it good? Would you like it? Just have a glimpse at it. Just think about it. The two fluids, they are exchanging, but the two fluids are flowing in the same direction. That is parallel flow. And it's not good. I hope that's what you thought. It's not good in a way that, yes, the concentration gradient is going to be steep at first. Okay? In that, let's say this is the fluid that is flowing towards this side and is flowing in this pipe, and this is another fluid, and the two pipes are in close contact, and this one is flowing towards this side. Okay? And this is, let's say this is hot water, okay, at 100. This is boiling water at 100 degrees Celsius, and this is cold water at 0 degrees Celsius. I don't know how this water is going to move, but assuming. So by the time these two, this one reaches here and this one reaches here, the concentration gradient means difference in concentration is going to be so high, so high, so high, that the rate at which exchange is going to occur here, it will be so high, so high. Okay? Because the concentration gradient, I mean exchange of heat, heat will diffuse from here to this at a faster rate. But as you keep progressing, then the water here will become colder, will become cold, okay? Colder as you progress, and the water here in tube 2, it will keep warm, becoming warm. It will be warmed. That you reach a given level, okay, maybe it's here, where the two waters, yes, the two waters are in equilibrium, are in a dynamic equilibrium. So the same applies with blood. Maybe they are all at 50 degrees Celsius. And the same applies with this current, this countercurrent, this concurrent flow or parallel flow. In that, since blood is flowing in the same direction and water is flowing in the same direction, then you reach a level where you attain the same concentration. You attain the equilibrium. And so what does that mean? Some parts of the gill plates, or some gill plates, in other words, or some parts, they are less, they are not supplied. Okay, they are supplied with that water, but the blood that is flowing through has the same concentration of oxygen as water that is flowing through. Okay? Let's have a look before I talk about these statements. So this is your gill, this is your shark, it's swallowed water and water is flowing through. This is blood and blood is also flowing through. But the water, as water is flowing through the gill plates, like how you can see, it will flow in the same direction as blood that is flowing through the gill plates. They will be in the same direction. That's how this apparatus is arranged. It is arranged in such a way that blood and water that is flowing through the gill plates, they flow in the same direction. Now, the concentration gradient at first is going to be so high, steep, that this, you can have a look at the graph, that the water that is flowing through, it will have a high oxygen, but the blood that is flowing through at first, it will have low oxygen and high carbon dioxide. So as you are extracting some oxygen from water, yes, the concentration of oxygen in water is going to decrease, like how you can see this. And the concentration of oxygen in blood is going to increase, like how you can see this. That if you proceed, you reach a level where the two are in dynamic equilibrium. The two are in a dynamic equilibrium. Sorry for that. You have a look. Let's say you have 90% oxygen and here you have 10%. Yes, the 20 will diffuse into, and this one becomes 30 and this one becomes 70. Still, the concentration gradient is still there. Okay, then the 20 will diffuse and this one becomes 50 and this one also reduce and become 50. So now it is the same. The concentration gradient is the same. It is the same. Not so? And so you reach a certain distance of a gill plate and the concentration gradient is 0. And remember, we call that one a dynamic equilibrium. So the rate at which oxygen is leaving blood into water is equal to the rate at which oxygen leaves the water into blood. And what does that imply? You won't extract any more oxygen. And is it good? You need oxygen. Is it good? I don't know. We shall see. We shall compare. So as a result, this is not an efficient system of absorption, but that's how it was. That's how it is organized. That's how the apparatus is. It's not an efficient system in that the fish won't be able to extract enough oxygen from the water to meet its physiological demands. And so the fish also is smart enough. It has devised means, okay, of obtaining oxygen, even with such, let me say, comorbidities, okay, in such disadvantages. Yes, it is at a disadvantage, but it has also learned to live with such a disadvantage. The same as corona, it's a disadvantage, but we should also learn to live with corona. regardless of it being a disadvantage. So these organisms, they almost move when their mouth is widely open. Hmm? They move when their mouth is widely open and they close it during exhalation. So why? So that at any time t, the speed at which water moves through these gill plates is high. You supply these gill plates with enough water content so that at any time t, yes, you will reach the equilibrium, but water flows at a high rate. Okay? So you try to extract oxygen at any time t that is enough to sustain your body survive. So that is the parallel flow, okay, or the concurrent flow. And you can try this at home. Get two tubes. One you pass there hot water, in another you pass there cold water. And all of them are flowing in the same direction. Then you get another tube. One you pass there cold water, another you pass there hot water, and the two flow in opposite direction. You'll be able to testify. Okay? You'll be able to understand this. So now, let's talk about the bony fish. Now these ones, they are, let me say, they are kinda advanced from their fellow counterparts. They are advanced as compared to their fellow chondrichthyes. In that the mode at which they obtain their oxygen. Yes, the inhalation and exhalation is the same, but the mode of extracting oxygen is totally different. And even the gills are different. For instance, here the gills are covered by the opaturum. So they are protected and they are supported. The gills have a gill bar, which is, I think, is it bony? I think. Well supported. You have gill rackers, the gill filaments with no septum. Gill filaments here don't have a septum. They are not separated by a septum. The so-called gill filament, not separated by a septum. Okay? And so they are, let me say they are open. They are in form of a V. And actually it is that V shape that maintains the flow of water through the gills. And it's actually that gives the water to flow in opposite direction as blood. Anyway, let's have a look. Let's have a look. This is not Kujura. Yeah. Anyway, that's Uganda. So gills of pterocysts are protected by the opatula. All of you, if you have ever seen a fresh fish, you know what the opatulum is. Okay? You know what the opatulum is. That hard stuff. Okay? With gills inside. Hmm? These ones. These are the gills. Do you eat them? Some of you cannot touch the gills because they are slimy, too soft. Mucus, covered with mucus, that's slimy. We can say mucus. That appears so disgusting. But to the fish, oh, yeah, that's how they survive. That's how they survive. Okay? So the opaturam, it protects the gills, okay? And gives them to the site that I got it from. So the opaturam, it protects the gills, okay? And gives them that physical support, physical protection. Now the existence of the opaturam, unlike with chondrichthyes where we saw they are just pouches with small slits, gill slits. Here the opaturam, there are things that you lose. Number one, you renders branchial valves useless. The other extension, they are rendered useless in this case. So they are lost in teros. In bonefish, they don't have the branchial valves. The septum, useless. So that it is completely lost. That the gills, these filaments, they are just very many filaments, fibrous. The lamella fibrous, not bound together. Okay? To allow easy flow of water through the gills. The two sides of each gill, they are separate, they are apart. Okay? They are apart. And so this separation gives them a V shape. Okay? And a V shape allows water to flow through gill lamellae and gill plates in the opposite direction. As blood flowing through the gill plates. And this is so important. This is some unique feature to bony fish. Okay? And so blood that is flowing through the gill plates, it will flow in the opposite direction as the water that is flowing through the space. The space is in the gill plates. So as a result, and we call that one the countercurrent flow of exchange, of gas exchange. And as a result, you will extract as enough oxygen in the water as it carries. So if the water is 99% saturated with oxygen, then blood that leaves the gills, it will leave when it is 98 or 99% saturated with oxygen. Unlike in the parallel flow, where blood leaves when it is 50% saturated with oxygen. We are going to see to illustrate that. So the adjacent gill filaments, they do overlap each other at the tips, offer resistance towards the flowing water, or the water that is flowing through the gills, so that water flows there at relatively lower speeds to allow efficient absorption, efficient extraction of oxygen from the water. And so obviously, water will flow down its concentration gradient oxygen will flow down its concentration gradient to the gills or to the blood, and oxygen and carbon dioxide flows down the concentration gradient to the water, and exchange occurs. And basically, this is what we are talking about. I like this, try to zoom in, and we have a look. So you can have a look at what we are saying. So the gills, they are just open space. These gill lamellae, these gill filaments, they are just open space, which gives them that V shape. So water easily flows through these gills, these gill spaces, these gill filaments. And as water is flowing, it flows in the opposite direction as blood that is flowing through the water. You can have a look. So you see, this is blood and the blood is flowing towards this direction. Okay, red in red. Let me change the pen. What is wrong? Maybe, okay, this one. It will work for us. So this is blood that is flowing, and the blood flows in the opposite direction as the water that is flowing through the gills. So blood flows in the opposite direction as water that is flowing through. So you have a look. If water and blood are in close contact here, you see, at this point, the water, let's say, is going to be like 10%, and the blood is going to be at 5%. So still the concentration gradient is maintained. Towards here, blood is going to be at around 80% and water will be fully saturated 100. So still oxygen will diffuse from water too. Maybe let us illustrate this. Let's illustrate this. So using the same tube, you have your two tubes. One is flowing like this and one has hot water at 100 degrees Celsius. So it has hot water and the water is at 100 degrees Celsius at this stage. Then this one, the two tubes are in close contact and the water here, it is at 0 degrees Celsius. Okay? And the water is pushed to flow in this direction. And here, this water, you can try this at home also, is pushed to flow in this direction. So the hot water here, as it is flowing through, how will this blood going to be? Is it going to be cold or it will be kind of hot? So if water here is at 100, the blood here is from this region, and the region received some hot, but not as hot as this. Now this one requires some logic. I don't know if you can see this. The blood that is at this point, or the liquid that is at this point, is from this point that was in contact with this liquid that was at that point. And this point, the liquid is cold compared to the liquid at this point. And still, this liquid therefore is going to be cold compared to the liquid at this point. The same applies to this. You see, this one, it is purely zero, but this can't be purely zero. Okay? It will be it will be some warm liquid here, okay, from one warm liquid where some heat was extracted and it proceeds. So it is relatively warmer than this one, which is too cold. So still heat will continue to move towards this direction. It is some logic. I don't know if you can see it, but I pray you see that logic. So what does that mean? At any time t, a concentration gradient is maintained throughout the tubes. And graphically, we can represent it as this. I don't have the graph. Oh, it's down. It's okay, we shall find a graph. Okay? Yes. Now with inspiration, it's the same thing. The flow of the buccal cavity is lowered due to the contraction of the mouth muscles. And if you lower the flow of the buccal cavity, what happens to the volume? Yes, think through. Then the volume is going to increase. And then what happens to the pressure? Pressure decreases. And then what happens to water? Water flows from the surrounding environment through the open mouth to the buccal cavity. And then what happens when water is in the buccal cavity? Then the mouth is going to close. Okay? Now at the same time as water is flowing, the outside water presses against the opaturum. Okay? You have the opaturum here. And when you press against the opaturum, it will close the opatula here. Okay? So that the opatular valve closes. And so when it closes, then the water will fill the buccal cavity here. Now, after water has filled the buccal cavity, the opatular muscles, obviously they will contract, and the opatular will move outwards. It will bulge outwards. And when it moves outwards, what will happen to the opatular cavity? this space, this cavity that is covered by opatulum, where you have gills, the opatular cavity is going to increase, to enlarge. The volume inside the opatular cavity is going to increase. And if the volume increases, what happens to the pressure in the opatular cavity? It is going to decrease. And if the pressure in the opatular cavity decreases below the pressure in the buccal cavity, then what happens? Then water will be forced to move from the buccal cavity to the opatular cavity. Okay? So water is forced to move from the buccal cavity to the opatular cavity. And so when water fills the opatular cavity, it will be forced to move through this system of gills, numerous gills, through the gill plates. They also do have the gill plates. Okay? And as water is flowing through the gill plates, okay? As water is flowing through the gill plates, my pointer, it will be in close contact with blood capillaries. I'm not saying water will be in contact with blood capillaries. So somebody will ask, how about mixing? No. Water will be in close contact with blood capillaries, and so the respiratory gases will be exchanged down their concentration gradient. And blood extracts oxygen from the water, and water extracts carbon dioxide from blood and taken outside the surrounding water, and oxygen taken throughout the fish body for respiration. Then after exchange has occurred, then you're going to push out that water from the opatulum. Okay? Through the opatulus, the opening in the opatulum, and water is pushed out. So the mouth must close, the floor of the buccal cavity is raised, the volume reduces and pressure increases, and then the opatulum moves out inwards to reduce the volume of the opatular cavity and increase the pressure. Then what happens? Water is pushed out of the opatular cavity through the opening, through the open opatular valves. Okay? And then carbon dioxide together with the toxic metabolic wastes like ammonia or trimethylammonium, depending on which fish, is excreted out through the gills, or into gills, and then exhaled out through water that moves out when the opatulam opens. So basically, it's that simple. It's that simple. So now for the countercurrent flow mechanism, this one is an efficient flow, like how we have seen, whereby the two saturating liquids are flowing in different directions, in opposite directions, whereby the water that is flowing through the gills and the blood that is flowing through the gills, the gill plates, they flow at opposite direction. And so the oxygen that is saturated in water, you have 80 to 90% saturation in water, is going to be extracted. That almost all, if not all, is going to be extracted from the water because the two systems are flowing in opposite direction. Okay? Why? The diffusion gradient is going to be maintained. We are going to see how. And so because of this, you're going to extract enough. Have a look at this. So this is your fish, and these are the gills. Water is flowing through and blood is going to flow in opposite direction. So as water is flowing through this direction, the blood is going to be flowing in this direction. Okay? Now, like the other illustration I gave you. So if blood that is entering into the gill slit, the gill plate, has okay, let me say 5% saturation of oxygen. The water that is leaving here, it will have something like 10% saturation of oxygen. So the concentration gradient is there. So the oxygen can still diffuse, okay, from the water into the blood. Even when blood is leaving, even when blood is tired, that it's like, oh man, I'm now tired, let me leave. Even when it is leaving here, it will be at something like 89% saturation. And the water that is entering at this point, it will be at 90% saturation. So there is still that difference. So you still take in some oxygen and you leave when you are 90% saturated. Boom. Anything hard? Obviously no. So therefore, the graph is going to be like this. Okay? So this is distance along the lamellae or the gill plate, and this is percentage saturation. And at any point, this is at the entry, okay? The blood, this is percentage saturation, okay, of oxygen. So the blood, it is going to be here when the water is here, okay? And you can see the blood is little, the concentration of oxygen in blood is less, but the concentration of oxygen in water is also less. But at any point, maybe point X here, the concentration of oxygen in blood is always low compared to concentration of oxygen in the saturating water. Take a look at this point. The same. This is blood and this one is water. So at any point, the concentration of oxygen in water is higher than the concentration of oxygen in blood. So because of that maintenance in concentration gradient, you will this system is going to be efficient as far as extraction of oxygen is concerned. Okay? This system is going to be efficient as far as extraction of oxygen is concerned. Not so? Which maintains an efficient supply of oxygen to the entire body compared to the parallel flow.